Welcome back to Physical Science 101. In this lesson, we're going to talk about nuclear reactions, which are all the ways that one nuclear isotope can become a different nuclear isotope. The first rule for nuclear reactions is that in a nuclear process, the total number of nucleons cannot change. So the total number of neutrons and protons that we start out with have to equal the total number of neutrons and protons that we end up with. However, a proton can change into a neutron and vice versa. Now when that happens, another rule is that the total charge has to be conserved. So for example, if a neutron turns into a proton, that satisfies the first rule because the total number of nucleons has not changed. However, it doesn't satisfy the charge conservation rule because we started off with a neutral neutron and it turned into a positive proton. So we started off with zero charge to begin with and we end up with a positive charge. So what that tells us is that in that process, we also have to create an electron to conserve our total charge. So it is allowed for a neutron to turn into a proton and an electron. Let me draw you a diagram of that. We'll start off with our neutron, and that will turn into a proton. So our neutron turns into a proton. That satisfies our first rule. So we have the same number of nucleons. We have one nucleon to begin with, one nucleon to end with, but that doesn't conserve charge. So the neutron also has to produce an electron. Let me give the electron a little minus and the proton a little plus there. Okay, so the neutron becomes a proton plus an electron. And so that would be an allowed nuclear reaction because we conserve our number of nucleons, one nucleon, and we conserve charge. Zero charge to begin with, zero net charge to end with. So this is an allowed nuclear reaction. A neutron can turn into a proton plus an electron. Now one more thing to talk about here is if you remember when we talked about a rifle shooting a bullet, because the rifle had more mass, it was the bullet that wound up going faster. And the same thing happens here. The electron has much less mass than the proton, so when the neutron releases the proton and the electron winds up going very fast. So this becomes radiation. This electron that is released is called a beta particle. So the electron goes shooting out. And this electron is called a beta particle. So this process of a neutron turning into a proton and shooting out an electron becomes beta radiation. Or beta decay is another way. Beta emission, beta decay, those are a lot of ways of saying that. The key there is that the electron is the beta particle and it gets shot out of the nucleus like a tiny bullet. So this is your first experience with radiation. This is beta radiation. Now the same thing can happen for a proton becoming a neutron. So I'll draw that. So we have a proton. That can turn into a neutron. Okay, that conserves our number of nucleons, but it doesn't conserve our charge. So somehow the proton has to shoot out its positive charge, and it does that as an anti-electron, so a positive electron. So when a proton becomes a neutron, it also shoots out a positive electron, also called a positron, okay, positron, And if you've ever had a positron emission tomography scan or a PET scan, that positron is referring to positive electrons that are emitted in a process that is used to scan your body. So this positron is a beta plus particle, and this would be a beta minus particle. So a positive electron, also called a positron, is also called a beta plus particle. So this process would be beta plus radiation. So these two processes are both called beta radiation. We can have beta minus or beta plus. And the electron and the positron are also both called beta particles, either a beta minus particle or a beta plus particle. So this is the first type of nuclear reaction that we can have. We can have a neutron turn into a proton, or a proton turn into a neutron and shoot out either an electron or a positron, also called a beta particle. So this is beta emission. We have a neutron turning a proton, or a proton turning into a neutron and emitting a beta particle, either an electron or a positron. Another common nuclear reaction is when a nucleus ejects a helium-4 nucleus. So for example, let's start with a uranium-233 nucleus. So I'll draw it. Uranium-233 is this big lumpy nucleus, lots of protons and neutrons. So that's uranium-233, and it will eject a helium-4 nucleus. Now remember that a helium-4 nucleus has 2 protons and 2 neutrons. Helium-4. Okay, so the uranium-233 ejects the helium-4, so uranium-233 becomes helium-4, and then what is left behind? Well, remember that we have to conserve nucleons, and we have to conserve charge as well. Oops, it's a helium-4. There we go, helium-4. Plus what? Well, for this, we have to go to our periodic table, okay? And on our periodic table, uranium is element 92. So uranium has 92 protons, okay? What happens is that it ejects 2 of those protons in the helium-4 nucleus. So we start off with 92 protons, we shoot out 2 of them, and we're left with 90 protons. So if we have 90 protons, we go back to our periodic table, and we see that element 90 is thorium. So what's left has to be thorium. Okay? 92 protons minus 2 protons equals 90 protons, which is thorium, because thorium is element 90 on the periodic table. Okay? So that gives us our atomic number of 90 and our element of thorium. And what is our mass number? Well, we started off with 233 nucleons. We lost 4 nucleons, so we must be left. So 233 minus 4 must leave us with 229. 229 nucleons. So uranium-233 shoots out a helium nucleus and leaves us with thorium-229. Now, once again, the thorium is much more massive than the helium, so the helium is what goes shooting out like a bullet. The helium in this case is called an alpha particle. an alpha particle, and the shooting out of an alpha particle is called alpha radiation. Alpha radiation. So this process where a uranium shoots out a helium, which goes out like a bullet and leaves us with thorium, is our alpha radiation. Now, alpha radiation and beta radiation occur spontaneously whenever the result is a lower total mass energy. So the total mass energy of a helium and a thorium must be less than the uranium. Where does that energy go? That energy goes into the kinetic energy of the alpha particle, of the helium nucleus that gets shot out, or in the beta particle. So in either case, whenever we can turn a proton into a neutron, turn a neutron into a proton, or shoot out a helium, and the result is a lower total mass energy, then that process can happen spontaneously, and the result will be the shooting out the kinetic energy of an alpha particle or a beta particle. Remember that the mass per nucleon increases with atomic number for the higher atomic number elements. This means that the higher atomic number elements tend to decay into smaller atomic number elements through these two processes, alpha decay and beta decay. Now, there are actually 4 different decay chains that I show you here in this chart, and the reason why there are 4 chains is that alpha decay always changes the mass number by 4, and beta decay doesn't change the mass number at all. So there are 4 different chains, and the decay always stays in one of those chains. Now, another way that the higher atomic number elements can decay is that they can also just fall apart. And this is called spontaneous fission. And this happens when the element falls apart, the result is a lower total mass energy. So once again, if the uranium can fall apart into 2 lower atomic mass number elements, and the result is a lower mass energy, then that can happen spontaneously. So this would be called spontaneous fission. Now, we talked about alpha radiation and beta radiation. There's actually also gamma radiation. But the important thing to realize here is that gamma radiation is not particles, but a kind of fluorescence. We already talked about gamma radiation when we talked about light. So gamma radiation is a kind of light and a kind of fluorescence. And the important thing for this unit is that that does not change the makeup of the nucleus, because gamma rays are not nucleons and they don't have charge, so they do not change the nucleus. So if a uranium-233 nucleus gives off a gamma ray, it remains a uranium-233 nucleus. So gamma rays are not any kind of particle, they're not nucleons, and they don't have charge, so they do not change the nucleus. Now for some questions. Which one of the following is an electron emitted by a nucleus as it undergoes radioactive decay? A, an alpha particle, B, a beta particle, C, a gamma ray, or D, a zeta ray? The correct answer is B, beta particle. Remember that when an electron is emitted by a nucleus, we also call it a beta particle. Next question. Which one of the following is a helium nucleus emitted by a larger nucleus as it undergoes radioactive decay? A, an alpha particle, B, a beta particle, C, a gamma ray, or D, a zeta ray? The correct answer here is A, an alpha particle. Remember that when a helium nucleus is emitted by a larger nucleus, we call that helium nucleus an alpha particle. Next question. The nuclear reaction that takes place when a nucleus splits into more stable, less massive nuclei with the release of energy is called nuclear A, chaos, B, fission, C, fusion, or D, disintegration. The correct answer here is B, fission. Fission means splitting apart, and fusion means bringing together. So in this case, when the nucleus spontaneously splits, that would be nuclear fission. So the correct answer is B, nuclear fission. Okay. The ejection of a beta minus particle, which is an electron, from a nucleus results in A, an increase in the atomic number by 1, B, an increase in the atomic mass by 4, C, a decrease in the atomic number by 2, or D, none of the above is correct. Now for this one, please pause and think about it and work it out, and when you have an answer, then hit play again. Okay, remember that when we have beta minus decay, we start with a neutron and it ejects an electron, a beta minus particle, and the neutron becomes a proton. So the neutron becomes a proton plus an electron. This gives us an extra proton in the nucleus. So we have an extra proton in the nucleus. That increases our atomic number by 1. So the correct answer here is that the ejection of an electron, a beta minus particle, from a neutron in the nucleus results in having an extra proton, results in increasing the atomic number by 1. So the correct answer is A. This results in an increase in the atomic number by 1. Next question. The ejection of an alpha particle from a nucleus results in A, an increase in the atomic number by 1, B, an increase in the atomic mass by 4, C, a decrease in the atomic number by 2, or D, none of the above is correct. So once again, please pause and think about this and work it out, and then when you definitely have an answer, hit play again. Okay, let me draw a picture. We start off with a nucleus, and that nucleus emits an alpha particle, or a helium-4. And what we're left with is something with 4 fewer nucleons and 2 fewer protons. So we are decreasing the mass number by 4. And we're decreasing the atomic number by 2. So we took away 2 protons. So we decrease by 2. So when this nucleon shoots out the helium-4, we lose 4 nucleons, which decreases our mass number by 4 and decreases our atomic number by 2 because we've removed 2 protons. So the only one of these that is an option given to you is C, a decrease in the atomic number by 2. So the ejection of an alpha particle from a nucleus results in a decrease in the atomic number by 2. Next question. The emission of a gamma ray from a nucleus results in A, an increase in the atomic number by 1, B, an increase in the atomic mass by 4, C, a decrease in the atomic number by 2, or D, none of the above is correct. So once again, please pause and think about it, and when you have a definite answer, hit play again. Okay, the correct answer here is that none of the above is correct. Remember that a gamma ray does not change the atomic number or the mass number. A gamma ray is a form of light, and it does not change either the number of nucleons or the number of protons. So none of the above is correct. So the correct answer is D. Next question. An atom of radon-222 loses an alpha particle to become a more stable atom of A, radium, B, bismuth, C, polonium, or D, radon. Now please pause and consult your periodic table, and when you're ready, hit play again. Okay, now remember that when you eject an alpha particle, you lose 2 protons, so the element number decreases by 2. If we look at the periodic table, radon is element number 86. So when it loses 2 protons, it becomes element number 84. And element number 84 is polonium, so the correct answer is C, polonium. Next question. Hydrogen-3 emits a beta minus particle, and the new nucleus formed is A, helium-3, B, helium-4, C, hydrogen-2, or D, hydrogen-3. So once again, please pause, draw a diagram, and think about this, and when you have a definite answer, hit play again. Okay, let me draw hydrogen-3. Hydrogen has a single proton, and since it's hydrogen-3, it must have 2 neutrons. So this is hydrogen-3. Hydrogen-3. Hydrogen, element 1, has 1 proton, 3 nucleons. So that must be 1 proton and 2 neutrons. Now, beta minus decay, remember, is that one of these neutrons will shoot off an electron. So that is a beta minus particle. So that's beta minus decay. So what's left, well, when that neutron shoots off this negative charge, it becomes a proton. So we go from 1 proton and 2 neutrons to 2 protons and 1 neutron. 2 protons, that's element 2, that's helium. But we still have 3 nucleons. So hydrogen-3 becomes helium-3, So the correct answer is A, helium-3. Next question. A nucleus emits a beta plus particle, and the number of nucleons it contains is now A, greater, B, fewer, or C, the same. Now please pause, think about it, and when you have a definite answer, hit play again. The correct answer is C, the same. Remember that the beta plus emission changes a proton into a neutron, but the total number of nucleons is the same. So beta emission does not change the number of nucleons. So the correct answer is that the number of nucleons is still C, the same. Here's our last multiple choice question. Which of the following is most likely to happen to an alpha particle after it is emitted? A, it escapes to space where it is known as a cosmic ray. B, after being absorbed by matter, it is dissipated as radiant energy. C, after joining with subatomic particles, it finds itself in a child's balloon. Or D, it joins others of its kind to make lightning and thunder. The correct answer here is C. After joining with subatomic particles, it finds itself in a child's balloon. The alpha particle, the helium nucleus, joins with electrons, which are also subatomic particles, to become a helium atom, and it might find itself in a child's balloon. That is actually where our helium on Earth comes from. All of our helium on Earth comes from radioactive decay, alpha decay, in the Earth. So a uranium, say, will alpha decay. That alpha particle finds a couple of electrons, becomes a helium atom, and will collect in pockets in the Earth. And when we drill for oil, we tend to find helium as well. So our helium production comes from oil production in the Earth. So radioactive decay, alpha decay, gives us helium nuclei, which become helium atoms and collect in the Earth, and we will mine for that, and then we will make all of the uses that we make of helium. But every helium atom that you have here on Earth was once an alpha particle. So the correct answer here is C. Now, I would like you to please write a nuclear equation for the decay of all of the following nuclei as they give off a beta minus particle. So iron 56, beta minus decays, beryllium 7, and copper 4. So write an equation for what these nuclei become after they give off a beta minus particle. Remember what beta minus decay is. Remember that it is a neutron becoming a proton and giving off an electron. So I'd like you to please pause and work on this and hit play when you're ready to see me work through it. Okay, so remember, giving off a beta minus particle turns a neutron into a proton. So the result of giving off the beta minus particle is that we have an extra proton. So let's start with iron 56. Iron 56, that gives off a beta minus particle. So that's our beta particle there. That's our beta decay. Now the result is that we have an extra proton. So we have to consult our periodic table. We have to see that iron is element 26. When we get an extra proton, that turns the iron, element 26, into element 27, which is cobalt. Okay, so iron becomes cobalt. The number of nucleons, the total number of neutrons and protons, doesn't change. So this is 56 neutrons and protons. We still have 56 neutrons and protons. Okay, so the iron 56 beta minus decays and becomes cobalt 56. Beryllium 7 beta decays, gives off an electron, and the beryllium, when we consult our periodic table, we see that that is element 4, meaning 4 protons. After the beta decay, we have 5 protons, which is boron. And once again, 7 neutrons and protons stay 7 neutrons and protons. So beryllium 7 becomes boron 7. And copper 64 beta decays. Copper is element 29. After beta decaying, it becomes element 30, which is zinc. And copper 64, 64 neutrons and protons, stays 64 neutrons and protons. So copper 64 beta decays and becomes zinc 64. Okay, this is our final question for our nuclear reactions lesson. Please write a nuclear equation for the decay of the following elements as they undergo alpha emission. So please pause, work it out, and when you're ready for me to work through it with you, hit play again. Okay, uranium 235 undergoes alpha emission. The alpha is a helium-4. So uranium 235 ejects a helium-234. That helium-234 takes away 2 protons with it. So whatever's left has 2 fewer protons. So our atomic number will decrease by 2. We look at our periodic table. Uranium is element 92. It loses 2 protons, so it becomes element 90. Element 90, consulting our periodic table, is thorium. Okay, so uranium becomes thorium. And we also have lost 4 nucleons. So we have 235 nucleons to begin with. We lost 4 of them. So uranium-235 becomes thorium-231. So uranium-235 ejects an alpha particle and becomes thorium-231. Radium-226, once again, ejects an alpha particle. That's a helium-4 nucleus. Radium, consulting our periodic table, is element 88, so it loses 2 protons, becomes element 86, which is radon. So radium ejects a helium, becomes radon, starts off with 226 nucleons, so it must be left with 222 after it ejects 4. So 222 plus 4 gives us our original 226. So radium-226 alpha decays and becomes radon-222. Plutonium-239 alpha decays and becomes plutonium is element 94, consulting our periodic table, becomes element 92, which is actually our uranium. And 239 minus 4 is 235. So plutonium 239 alpha decays into uranium-235. Okay, so those are our nuclear decay processes, including radiation, alpha radiation, beta radiation, and gamma radiation. And the next lesson, we're going to talk about radioactivity and its effects on the body and radiation safety. Until then, think science.